Good morning, everyone, and welcome once more to our lecture on Introduction to Finite Element Methods. This being our fourth lecture, this fourth or fifth. We've looked at the spring element, the illustrative tool. We've looked at the bar element, both in 1D and oriented in 2D space. And today we look at the beam element, that type of an element. Now, so far so good. Sorry for that delay. My computer was updating something on my computer, which took quite some time. But that being said, I believe today will be a short one. So sit back, take your pen, let's learn together. So far so good. All right. That's okay with checking the audio. So when you talk about the beam element, if you recall, whatever you have been looking at, whether it be the spring element, whether we are talking of the spring element. Let me just make this large screen so that you can be able to see this clearly. Whether we are talking of the spring element, okay, where maybe the head was fixed, then we applied a load P there, or we are talking of the bar element, where we are assuming, let's even say that it have got a different changing cross section, okay. Whatever it is that the load was applied, or even if we had, when we considered the bar element oriented in 2D space, okay, and let's assume this side is fixed and the load was applied. So in all these things, what you considered is, or what you noted is that we are talking of load applied axial. So we are talking of axial loading. So axial loading. So what you expect was the reaction to be, of course, the axial reaction, the F on the X direction. If we take the normal X direction to be this horizontal, okay. So the deformation was extension, actual deformation, extension, elongation, elongation or compression, reduction in length, right? For bar element. And the load was applied axially. Now, for the beam element, what you have to consider by definition, beam element are long and the slender. These are long and slender elements, structural element. And when you talk of long and slender, sometimes we define in terms of ratios of cross section. Okay, because you have something like this, and then you have this length. Okay, this being the depth. Then we have the breadth, of course, and then this is the length. Okay, there is this now. This is a beam. Okay, you could also have the same a slab have got the same dimensions, but the thickness, the ratio thickness reduces, like a slab, something like that. Then you find this is the thickness. We call it T, which is the breadth, of course, D, and then this is the width B. Of course, when you are designing this, we take it as 1 meter. Then this is the length per meter run. Again, if you change the ratios, you can have a plate. Plate is very thin, but the geometry is the same. Okay. So for the beam, we define them as long, slender structural member, generally subjected to transverse loading. So in this case now, we are saying the beams are generally subjected to transverse loading. I think I can remove this video to have more space. Okay, so let me create our drawings. Okay, this why. Okay, so you can just erase. Maybe I'm using two tools. All right. Seems my laptop is hanging again. This is a problem I was facing in the morning. Don't know what we do about this. Okay. Sorry for that. Because if I cannot clear my workings, then I won't have space to do more work. Okay, seems like you're not working, but I just wanted a space to highlight a few issues. Now we are saying for the beam, now for your beam, we are saying number one. This now as opposed to the bar element which carries the axial load, beams. So if we take this being our beam member there, so the beam is supported there and supported on this point. So the beam is usually subjected to transverse loading, transverse as opposed to axial. Okay, axial of course is along the axis of the member. Like this is perpendicular. So transverse loading, it could be a point load, it could be a UDL, uniformly distributed load, whatever that be the case. Then this loading, because of this nature of loading, the transverse load, what you expect, of course, there is the action, which is the load. The reaction would be, or the output, this causes bedding. So this one will cause bedding, okay? Based on, of course, fixity here. That's why I'm sketching like this. If this side was fixed, if it was just what you say simply supported, then there will be rotation here on this edge, okay, like that. So this bedding, there will be no twisting or the axial effect as we expected in the bar. Of course, twisting is brought about by moment. So the bedding deformation, our bedding now is measured in terms of this displacement, the transverse displacement. Our bedding will capture it in terms of this vertical displacement, which we are calling the transverse V, as well as the rotation at the support. Of course, if let's say I'm saying if this is simply supported, we talk of the rotation here. Of course, if it's fixed, if your beam is built in here, okay, then it deforms like that. Then there's no rotation of the support. Okay, I know you already know this because you've been handling much about beams and different kind of supports. So therefore, we consider that for the bar element that we are talking about, there was only 1 degree of freedom per node. 1 degree of freedom element in the local coordinate system, of course. So which was the transverse displacement? Okay. Now, no, the axial displacement. But for the bar, for the beam element, the degree of freedom is that you have the rotation theta, and of course the vertical displacement V or dy. So there will be transverse displacement as well as rotation. So there are some assumptions that we make in deriving the finite, because of course you know the finite element equation, which you call the equilibrium equation, is equals to F is equals to K delta. Okay, so the first step is usually determining the stiffness matrix. Okay, so we'll be tasked with given the task of deriving the stiffness matrix for a beam element, which for this class I'm not going to dwell much into details, but you can always refer to some materials that I've shared in this platform sometimes back. But it should not be difficult. What I want us to know today is a few assumptions that are made for this derivation from elementary beam theory. Of course, most of you might have gotten, but from the theory of simple bedding, this is when you derive this equation. Should be in the strength of materials, or material mechanics, or structures, whatever you know the course code might have been called for different people. So M of I is equals to F of Y is equals to E of R. Okay, E of R. So this is when you derive this equation. This is what we call the equation of simple bedding from the beam theory. So the assumption is, just as we had the assumption in the spring, the assumption in the environment, in this case, we have the first assumption that the beam is loaded only. So our beam will only be loaded okay. So the beam, before we come to the sign convention, we are saying our beam, this is our beam. Okay. So the beam is loaded only in the y direction. So we have this axis as a y, and then we have this as the x. So the beam will only be transverse. The loading will only be transverse. Then number two, of course, deflection of the beam are small in comparison to the characteristic dimension of the beam. So we are talking of small deformation. You become to understand the theory of small deformation and large deformation. So we are saying this deformation delta is small. This is small compared to, of course, the length or the dimensions of the beam, the length, the L, so that we are within what we call the small deformation theory. Number three, we assume a material which is linear, elastic. And this is a feature that is important to understand. When we talk of a material which is linear, okay, then we say it's elastic or linear elastic. Then we talk of isotropic. Then we talk of homogeneous. This is our perfect material that we are considering. Of course, linear meaning that it obeys the Hooke's law, F is equals to. Of course, a material that we are dealing with in the finite element analysis, it's kind of have to obey this. Otherwise, you might not be able to derive the equation. Our equilibrium equation is based on this fundamental equation, the Hooke's law. So it's for linear elastic range. Then elastic, of course, this is what we are talking over. Then isotropic. I wanted to differentiate between isotropic and homogeneous. Isotropic material is a material that is uniform in all direction. Consider a case like concrete cube. So this is concrete cube. Okay. So if you do the compression test, it doesn't matter whether you test this cube. Let's call this face A, and then this face B. Even if you turn it the other way around, that the face B comes on top. Okay. The face B is on top. The face A now is here. We expect the strength to be the same for concrete. So the material have got uniform characteristic in all direction. So it's isotropic. But this will not be the case for a T-bar. Remember, let's say you take a cross-section from a T-bar plank. Let's say you have a long section of a T-bar. Then you take some pieces. So this one, you are testing it for maybe compressive strength. You apply the rod here, and the grains are running like this. Okay. This will be different if you take the same piece. The grains are running like this, and then you load it across the grain. And that's why for T-bar, a design of T-bar structures, we always specify whether the stress given is maybe the permissible stress along the grain, across the grain, and so on and so forth. So we talk of T-bar being, yes, homogeneous, but it's not isotropic. The characteristics of the material are not uniform in all directions. So that should stick into your mind. And we have many examples, many materials having that characteristics that you find that they have one in one direction is so strong, but in the other direction, which we try not to utilize, maybe it's weaker. Now, when we talk of derivation, of course, there is the issue of the sign convention. So in this, there are a few things that you have to note in finite elements when you are deriving the stiffness matrix and the finite element equation for the beam element. The issue of the sign convention as opposed to what you have been considering for the case of the normal beam theory. So when you are deriving about equation in the beams, you talked of your beam being like this. Okay, you talked of the moment that cause, or we call them the hogging moment and the sagging moment. This is a sagging moment because it caused this beam to sag like this. Okay, maybe you may have you may still be remembering that. If not, just we are refreshing. If the moment were like this, which you call the hogging moment, they would cause your beam to deform, to deform like that. Okay, so let's stick with the sagging moment. And so we are saying, for purposes of sign convention, you are talking of for the sign moment for the bending moment that cause the beam to bend concave upward, like the way we have it here. So this one we talked of them being a positive sign convention. This moment are positive moment. Number two, the shear forces were positive if they cause a beam to rotate clockwise. So if the shear force is clockwise, of course, it's like this. So if that is the shear force, then the other one have to come like this. It's kind of they made a couple. So this is when we say that these are positive shear forces. Positive V, capital V. Remember, small v, we are using it for this vertical displacement. But when we come to the theory, or when it comes to the derivation or when we are dealing with the finite element, beam as a finite element, then the sign convention changes slightly, because we say moments are positive in the counterclockwise direction. So you can see from whatever we had in these, what we had in this, let me get a different color. So what we had in this, yes, this is counterclockwise, so this would be positive in our case, but this is clockwise, so this would have been a negative moment. Okay, so we are saying for our beam, if our beam is like that, if you have a beam like that, then positive movement have to be in the same direction, counterclockwise. Number two, rotation are positive in the counterclockwise direction. Okay, so when you talk counterclockwise, remember we are measuring from the horizontal x-axis. Okay, so if like this is the deformation, if this is the deformation, let's say there is a rotation here like this. So we have this rotation here, theta, and the rotation of this support, theta. So this was simply supported. So if I am at this point, then I look at this. When I come at this node, I see this is in the this is the x direction, x coordinate. So this is on the negative side. It's clockwise. So this is negative rotation. Okay. While this, when I'm on this point, when I'm on this node, it means this is in the positive or is in the counterclockwise direction. Therefore, this is positive rotation. Okay, that's a difference. Of course, forces are considered to be positive in the positive y direction. You see, for the shear force in the normal beam convention, we were talking of the beam like this shear force being positive upward and this one being positive downward, because they make this beam to rotate clockwise. But in our case now, for the finite element, because this is downward, this force, shear force, then we expect it to be a negative shear force. So the sign convention, forces are positive in positive y direction. Again, displacement are positive in the positive y direction. So from this axis, so this displacement here would be negative dy or negative v. Okay, so that is the difference between the two sign convention. Now, with that in mind, you can go ahead and now have what we are talking of as the, I don't know why some of them don't want to get the rest, but we are not going to dwell on that. Okay, so with that, now we move ahead. We get the sign convention that we are talking about. This is just a summary of what I've just given. That the top one, the top sketch shows the sign convention for the case of the bar. I mean, for the case of the finite element sign convention. The lower sketch or the bottom sketch shows now the standard sign convention that you are used to in the beam theory. So we use the first. So that's so that you can see the first is showing positive component. The first one, this is showing when this is the x-axis. So it's showing. So this is showing like positive moment. You see the positive moment, they are counterclockwise. Then for this to be positive rotation, it have to be, it's bending on the bottom lower part, and then for this to be positive on this side, then it have to the rotation have to be above the x-axis so that it will be in the counterclockwise direction, positive. Then what else? The forces, of course, even movement, of course. The forces, you know, they are upward. Forces and displacement have to be upward, otherwise downwards, then they will be negative. So having understood that, so I was saying the above is FEA beam, and then the bottom is beam theory. So we take a sample or an element, beam element like that, and then we are showing it have got two nodes. At per node, we have 2 degrees of freedom, which is theta, rotation, and V, which is displacement, vertical, transverse displacement. And you have to note that, of course, input or the action bring about reaction. When you apply the nodal force in a member, pulled, external force, you expect deformation, axial deformation to be associated with the axial load. So in this case, the rotation will only is associated by movement. No, movement are the one which bring about the rotation, or vertical displacement is associated with the applied axial force, which can also be the reaction. So that's why you are seeing all these quantities. They are grouped together with how they are related. Rotation related with the moment, vertical displacement related with the axial applied load. You are given material characteristic. Remember, you said the stiffness matrix encompasses both the geometry and material characteristic. So E, Young's modulus, represents the material characteristic. I represent the geometry. Second, the moment of inertia. So node IJ. Okay. Of course, now this is the notation, what we are calling each and of these. Of course, you know, some of them we have used them before. L, I, E. Okay. V, again, remember the other time we are talking of U in the bar element where you said U varies. So you say it's a function of the length. So same case, vertical displacement. What are you talking about here? So we are saying in this particular case, let's say that there's the deformation that will occur. Let's assume theoretically some hypothetical deformation like that. So what we are saying is that from this length, we said any distance from the support here, let's call it distance x, so that at this point, x is equals to L. So we are saying at any one point, V is a function of x, okay? And that's why it's continue varying as the distance x changes. So this is what this expression means. Rotation, of course, this is from the theory bedding. Rotation theta is a first derivative of the displacement. Of course, the force F is a function of, and that moment, the same case, is a function of the length. So those are just a simple notation which shouldn't confuse you. Now, from the theory of bedding with that, you can utilize, and I can give some hints, because the other step now, you are going to use this to come up with stiffness metrics. So what you do, some hint is that you have the slope is already given here. So we already have the slope is given here. Then another thing is that the uniformly distributed load, which we call the moment mx, which is this part here, is the second derivative of the displacement. And now we include EI. Of course, we include the material characteristic EI, d squared v over dx squared. When you come to the shear force, which are these forces here, this F, or whatever you can call it, V, capital V, note that, is equals to EI d cubed x over dx cubed. And you can go on and so forth. And then the applied load, if you have a load W, which is the UDL, it's expressed as a fourth derivative of the slope, EI d this power 4x of not this is not x, this is v over dx is power 4. So the first step when we are deriving the stiffness matrix is to assume or select a displacement function. Okay, so either way, if you select that, you can select the displacement function either from this head, and then you try this equation to derive. Okay, but that's not the focus of today. So you can refer to some material I shared some times back. It's in this channel, so you can refer to it, how to derive the stiffness matrix for a beam element. Because when you do that, you're going to end up with this equation, where this part is the stiffness matrix. This is now the displacement vector. This is the force, nodal force quantities. Of course, now of the force here, we are talking of the applied nodal quantities, which is the moment and the external force. And as you can see, for each one of these now we have the axial or the lateral displacement and the rotation, lateral displacement and rotation associated with lateral displacement associated with the axial, the lateral force or the reaction, the rotation associated with the moment. Okay, so it's quite easy again to have a record of this if you partition this like this. Why have you, if you have noticed something, one of the features of the stiffness matrix is that they are symmetric. So if you take the main diagonal, you take this as the main diagonal, of course, whatever is below here can be mirrored. Number two, you can be able to partition them. Why? We are talking of an element with two nodes. So it's a node here and a node here. So we expect for equilibrium, when you take out this element, the behavior, the characteristic here and the characteristic here too, I mean, the quantities to balance. And that's why you find for a stiffness matrix, we are having like repeated quantities. So if you look carefully, you are seeing this first quadrant is the same as the last, with the sign introduced in the minor diagonal. And this sign as a result of course, after you derive, you're going to get this, but this comes as a result of the sign convention. Okay. Then you see this quantity is this quantity here, but of course this value, the only value that needs is this 4 becomes 2. And then of course now we have the sign on this vertical, the first column, and this quantity is this here with the sign now on the row, the top row. So that's just a way that I came up with to record these, because in an experimental setup, in an exam setup, you might be given these, but let's say you are doing your own calculations. Maybe you don't want to keep on referring to this. So some of these simple things, though in engineering we are referring, we usually do references. When you are even doing our design, we use the code. But let me tell you, when you start doing the design, let's say you are designing a multi-story building and they have got maybe a steel tower on top, and we have got Tiba, decking somewhere. You are going to be employing so many codes. So if you don't know some of these equations, you keep on flipping on pages so many times. So basically, it's good to have at your fingertips some of these simple, especially the simple expression, because there are some which are rather complex. So this simple one, then you find a way of recording on them. But I'm not advocating on cramming per se. It's just sharpen your memory, and that's it. So this is our stiffness finite element equation for the beam element, and the K can clearly be seen as such. Okay. So let's look with an example. Let's look to an example. We see the application of this. I'm moving quite fast because now you have already done a number of computation on the finite element using the bar and the streaming spring. So you are well acquainted with the steps or the stages that we follow in the solution or in solving these kind of problems. So we are given a beam as can be seen here, and then this beam is fixed. So this head is fixed here and is fixed here. Okay. Then there is some moment that is applied at the middle, and also a vertical load force P is applied. The material is given as EI. So even without further ado, if EI, we just know K for whatever element to be, because the material property is the same, it will be EI of L cubed into bracket. We talk of 12 6L, then 6L, 4L squared. I take this one here to have 12, 6L minus 6L, 4L squared. So I put negatives on the minor diagonal. Then again here we have minus 12, 6L, then minus 6L, 2L squared. Then I take this one here, and then I change the sign negatives to the row. This should be minus 12, minus 6L, 6L, 2L squared. So basically this is the, sorry for that. So that will be the sign. I mean, that will be the stiffness matrix for whatever element that you have. Then number 2, you look at all that is given, you have seen. So you're required to determine the deflection and rotation at the center node. So because of the applied load, we expect to have a deformation. We expect to have a deformation somewhere, a deflection. This is just hypothetical. Because of this movement, maybe you may have some different kind of deformation, but you're going to see from the values obtained. So we are to determine this v, small v, or you can say dy, and then we also require to get theta at this node. Now the first step, discretize and select element type. So element type we have selected is the beam. Discretizing, of course, we have the criteria that use for determining the node location. And I made a short review of this. I think I posted it this week. You can look at a short video that I made on how to select a node. It's a 9-minute video, short one. So we said one of the things is that at the support, we have a node. So this is another node. And the point of load application. So now it means this is node 1, node 2, node 3. Okay, that's enough. So you may have other criteria that you may use to locate nodes based on the cross section. So make sure you watch that. It will help you in understanding in a quick way the location of nodes. So you have 2 elements, and each of these elements have got K as shown here, because the L is, of course, is L for each one of them. So we move ahead now. With K1 and K2, we can do what we call the assembly of the stiffness matrix. And what you do for the global K, you just need to get, for the K1, you'll be having V1, theta 1, V2, theta 2. So for the K2, basically the stiffness matrix is the same, but now if this is K2, okay, if this is K2, why it is not selecting? So if this is K2 now, then here you have V2, theta 2, V3, theta 3. So your matrix will be containing V1, theta 1, V2, theta 2, V3, theta 3. So what we do now is just a matter of using the principles for imposition, compatibility condition. You can be able now to match K1 and K2 to come up with K1 is like that. K2, you can see they are the same. The matrices are the same, that they represent different quantities. Why are they the same? Because the material property is the same, the geometry, the cross section is the same, and the length is the same. So if you go ahead and have a global finite element matrix, so we have V1, theta 1, V2, theta 2, V3, theta 3, and you see the quantities which were, if you look carefully, these are the part that there was a sharing of nodes at V2, theta 2. That will be having some additions from this matrix, matrix for element 1 and element 2. Okay, so this is not by mistake. Element we denote them by a number and circle. Then nodes we do not, we just leave them the way they are. And then once you have got K, so this is the K, or this is the K. With that, then we have, this is the deformation quantities, the way we call it, whether you want to call it the delta, whether you want to call it the U's, and then this will be the F's. Okay, F is equals to KU. So with this now, you go ahead and solve equation, this equation. So to do that, we need to reduce it. Otherwise, the way it is, they have got so many unknowns. And we do that by invoking boundary value problem. And by invoking boundary value problem is that we are fully defining our problem. Because as I said from lecture number 1, that we are solving finite element method, we are solving a boundary value problem. So without defining the boundary conditions, then we have not fully defined our BVP. Right. So if you look at this, based on the support condition, this is fixed, this is fixed. So of course I know from your past experience, you expect this deformation to be like this. Okay. I'm enlarging it so that you can see it clearly. So because of this fixity, the rotation here, theta 3 is 0. The same case with theta 1 is 0. Again, this is fixed. You don't expect any vertical displacement of this. So V1, same case with V3 is equals to 0. Okay. So you just come here now. This one will be 0. This one 0. This one 0. This one 0. And now to simplify your equation, you remove the rows and the columns associated with the quantities having 0 values. So you remove all that, you are going to be left with the quantities for V2, theta 2, which is this part. V2, theta 2, associated with this part. Okay. So this is our boundary condition. Of course, we are given the quantities M2 is equals to M, and it's positive. Look at the sign convection. Remember the sign convection? Positive counterclockwise. Load, if vertical axis is this, so the load is applied downward, of course. So this will be negative. So the load F2y, the force in node 2 is negative P. The moment is positive. And then we have this as 0. So we have our reduced equation like that. Okay. And with this now, it's very simple. It's simple algebraic equation, simultaneous algebraic equation that you can solve very quickly. So you solve that. And I hope by now you have done proper practice in on the solution of simultaneous equation using the matrix method. Okay. How to get the inverse of this matrix so that on this side you only be left with the V's and the thetas, the degrees of freedom, theta 2, which is equals to like this. Of course, this we are writing in matrix form. This tells you that V2 is equals to minus PL cubed over 24 EI. And the theta 2 is equals to 3 LM or ML over 2 EI, 24 EI. Okay, it's only that we are writing it in matrix form. So with that now, you can clearly see, that we have obtained for the nodal unknowns, nodal degree of freedom for the node 2, V and theta. So we move ahead to determine or to evaluate the other unknown quantities. So this is a global finite element equation. We go ahead to obtain the reaction forces and the moment. And as you can see, of course, the V2 and theta 2 are unknown. Okay. So we can invoke F1, M1, F3, M3. In order that you obtain these quantities. So it's just a matter of going back to your original equation. So bear with me today, some of these things are not getting erased. I'm just hoping it's not the issue with the streaming platform. Okay. What we are saying is you just have to come here and as you can see, you have determined this quantity. You have V2, theta 2, you already know V1, theta 1, you already know V3, theta 3, you already know F2, M2. So to get the other reaction, what is remaining is F1, Y, M1, F3, Y, M3. So you can just take an equation which is the top row equation is the one that gives you F1Y. So F1Y is 12 V1, which is 0. Then 6 times 0 minus 12 times V2. So F1Y, actually we can even do it here. Like F1Y, you can quickly see. F1Y is This is a vertical reaction. Is equals to this minus 12 times this, because the others were 0. If you multiply the first one times this, 0. So this one you can only avoid confusion if you already know how to work out or to matrix operation, how to multiply matrix, open up. So this will be minus 12 V2, then plus 6L times theta 2. So plus 6L theta 2. Then the rest will be zeros. If you multiply 0 times V3 is 0, 0. So you are, if you do that, you're going to get what is F1y. Already we have determined what is V2. You have already determined what is theta 2. And this is what you are obtaining from this. So don't worry about what you are getting here. So this is we have only remained with the quantities that are necessary to determine F1y. F1y we have said is minus 12 times V2, 6L plus 6L times theta 2. And when you substitute what is V2 from what you have obtained here, and what is theta 2, which you already determined here, okay, then you are going to get F1y is equals to a quarter 2p plus 3ml. And you can go ahead, if m was given and L was given, you can substitute, and P was given as a numeric value. You can go ahead and substitute to get it as a single unit. Okay, and that's it. It's very simple. Solution for this is very simple. Once you have determined the stiffness matrix, the other part now, the procedures we follow, just the same way we did. Because the beauty about the finite element procedures, method of our solution or analyzing our structures, is that no matter how complex our structure can be, we can break it down into finite elements. And then, no matter what type of finite element we select, even when we are using software, the procedures followed are the same. Okay. The challenge becomes like when we have many nodes. Of course, this is we expect to have many nodes in a real structure, maybe. So you expect to have quite large matrices, which might be tedious or even impossible to handle by hand. And that's why we need the power, the computational power of computers. Let me mention something before we see another example. When we have uniformly distributed load, okay, so you have a case like that. We're talking of distributed loads, transverse. We have to convert this because we said loads are applied at the nodes. We need to convert this into uniform, what we call an equivalent nodal load. Okay. So to do this, we utilize what we call the work equivalence method. Yeah, work equivalence method. I know you have tackled the issue of principle of virtual work and so on. So we convert the uniformly distributed loads into fixed head reactions. And fixed head, of course, will be constituted of the shear forces and the fixed head moment. So the UDL will be replaced by concentrated node of forces. So this is a node, this is a node. So we resolve this UDL to concentrated node of forces and a moment, which will TED. That's why we are talking of it being equivalent. The node of force, the way you resolve them, or the way you apply them here. Sign convention is very important because they have to produce the same effect on the beam as the actual distributed load. Okay. So these statically equivalent forces are always of opposite sign from the fixed head reaction. You know, fixed head reaction was now what you've been talking of in the other finite element, other approaches in theory of structures or structural analysis. So what happens in this case that the sign convention is in the opposite direction. Okay. So if we have a case like this, the fixed head, if we are to get the fixed head reactions, they'll be like this. This is your beam, right? So this, of course, the UDL will be the load will apply Q L over 2. The shear force. Of course, we are taking half of this. We multiply by half the L. We are taking this multiplying by this length, which is L over 2. Then we apply it here, and we apply it. The same way we deal with our applied load, the UDL, for the normal type cases of analysis for what structures. Then for the fixed head moment or the reaction, we use the sign convection for the beams. Okay. So this will be QL squared or WL squared over 12. So why this sign convection? Remember, when you look at the way these loads are applied, they cause the actual reaction, it causes the bending like that. It causes the beam to hog, not to sag, right? If the load was applied downward, it would cause the moment to sag. So if it causes the beam to hog, then we use the sign convention from the beam theory, elementary beam theory, like positive moment, or these are the moments that causes, if they are applied at a node, they have to cause hogging. They have to cause this thing to concave upward. Now we are saying for the finite element, the sign is opposite this. So this, whatever you are seeing here now, the sign will be opposite. So basically, for our case here now, the UDL that is applied now, the sign convection will be, so this will be acting upwards, and then the same case loads and so on and so forth. Okay, but of course the load you'll have to apply down for the moment. Okay, so let's see with some example. I hope I have given some examples here. So this is what I was saying for the fixed head reaction. This is what you already know. So for the in beam in a finite element approach, so you see these apply loads W of a length L. Of course, I know resolving the load in terms of the forces, nodal forces, no problem, because it's just W L over 2. You apply it at the support. Of course, the load is applying downwards. That's okay. But for the moment, for the moment, you see, if we are using the standard, the normal beam convention, this moment causes sagging. So we would have expected to have positive moment, like this. You are applying like that. The equivalent nodal loading. I hope I'm not bringing any confusion to you here in any way. Okay. And I'm giving other examples here when we have maybe UDL, but it's varying. So these quantities is just a reminder, you can obtain them from textbooks. Some of them you might have derived them as quantities. Then when we have a point load, remember, we have a point load, we can introduce a node here. But again, if we do not want to have two elements, we just want to have one element, we can resolve this point load, we can take it to a support. You see, this is what we are seeing. You divide it by 2, and then the moment obtained are like this. Let me show you with this example. For this case, you see the load is applied downward P. This is a UDL. The material is EI, length L. Then you have to find the deflection and rotation on the free head. We expect this cantilever beam to deflect like this. So you are required to get, what is this V? Small v. Don't confuse small v with a capital V, because capital V is shear force. And that's why maybe in some books, this small v denoting lateral displacement could be denoted by dy. Okay. Right. So you have to get that, and also you have to get the moment, if there is any moment at the support. Of course, at the free head, there can't be any moment. So there will be moment developing at this support. Okay. So the first thing first is to resolve our applied loads, uniformly distributed loads, using work equivalence method to get nodal, equivalent nodal. Okay. So of course, for the case of the load, applied load is quite direct, because we are going to get the load here, PL over 2, half of it coming on this side, and half of it coming here at the support. So this F being PL over 2. Okay, acting in the same direction, of course, as the load, because it will produce the same effect. Now, for the moment, you see, this moment, you know, the load is acting downward. So what effect does it have on this? What effect you look at it have on this? The normal sign convection, we could say the moment causes the hogging. So in case of our finite element, it's the other way around. It's opposite. That's what I wanted to clarify from the other thing. Okay, that's why you have having the movement in the opposite direction. Hogging, this means it's bell like that. Sagging would have been like that, which we do not expect that. Okay. Right. So F, of course, now is given as PL over 2. You know that. The moment is given by this fixed head moment, you know, WL squared over 12 is positive. So equation, we have just one element. So quickly getting the stiffness, of course, you know it. Okay. Then V1 theta 1, you have only two nodes, V1 theta 1, V2 theta 2. And you go and solve this equation. You invoke the boundary condition. What condition do we have for this particular case here? You find that at the support, this head is fixed. Node 1 is fixed as a support. So we do not expect to have any vertical displacement. So F2y is equals to, not force, sorry. This is a V1 and also rotation theta 1 is equals to 0. Why? This is fixed support. So there will be no rotation at the start, and then it starts bending like that. So at exactly the support, there's no rotation. And so you're saying V1 theta 1 is equals to V1 and theta 1 is equals to 0. Then M2, because this is the moment applied here, we have already determined it here. Then F2y, you know this axing downward, so it will be negative F. Okay. So you substitute by even substituting this is equals to 0, this is equals to 0, you will only be left with this part. Okay. And with that, you can go ahead and have your reduced equation like this, and you solve for V2 theta 2. Okay. So V2 theta 2, again, it's expressed in matrix form, but you know this is V2 is this quantity here. Minus PL over 4, 8 EI. And then theta 2 is this quantity here. So what is required of you from these examples is to really make sure you do the hard calculation so that the concept sticks into your system. Okay. So again, now from the global finite element equation, you can go back and substitute. Already we have calculated the unknowns. We have what is V2 theta 2. We want to get the reaction, the support. So F1y, M1y. So we just need to come and utilize this first equation here to get what is F2, F1y at the support here. What is the vertical load and what is the moment, inbuilt moment at that support. So you find it like that. And you can see these are positive. So it means the reaction is upward. Why should it be upward? It's obvious. You see this load is applied downward. So we expect the reaction. This is the action. The reaction is upward. Opposite direction. Again, the moment, these are positive. This means it's counterclockwise like that. All right. So I leave you with something of a practice. You look at this equation. You are given required to solve using direct stiffness method. Excuse. And once you do the sketching, you calculate the moment. You can be able to go ahead and sketch the shear force and the bending moment diagrams. So what is given here? A load P is applied vertically downwards. This is aurora support, right? The beam have got a constant EI, so the material properties are the same. Of course, even looking at it, the nodes have already been indicated 1, 2, 3. So you have element 1, you have element 2. Okay, it's supported. This is fixed, so it means no rotation here. So by now you can even anticipate your something rotation to be something like this. To be something like this. Something, maybe. Okay. So go ahead. So what first you need to get is K. K is standard because here is the same. Then you get a combined stiffness matrix, so the assembly of the stiffness matrix for the structure. Then you invoke the boundary condition to reduce your matrix you solve for the nodal unknowns. Okay. So when you are told to solve the problem of plot cantilever, you are to determine the unknown nodal quantities. So in this support, we know we don't know the reaction. So you need to obtain the moment and the shear force or the vertical reaction. So at this, we know that we are going to have a rotation, theta. Of course, vertical displacement here is 0. So we are going to get what is theta 2. In this node 1, what is required is the V1, the displacement. Okay. So this is a solution. You should target to see whether you can get something like this. For the shear force, this is a typical case. And for the bending moment, it's something like that. Of course, before you get to this is the last stage. You have done all the calculation. Likewise. So another practice example you could look at is now a case here. Some of these have been solved maybe in the past years. But for your practice, it's good to go through them, do your exercises so that you get hands-on experience instead of solving all of them here on the screen. If there is any problem, then you can always raise it, then we address it together. Okay. So here we have introduced a spring. So this becomes interesting here because now with this spring, we have the fourth element. You see, we have the third element. We have the fourth node. We have node 1, 2, 3, 4. I'll make sure you watch that thing on that small video on location of node, because you'll not always be given this node. It's upon you to decide where you locate the nodes, and you might not have nodes in the similar location like another person, because we have even found like where we have a load. We know the load is applied at a node. If we want to have just that one node and they have that, we can resolve this first to the support, okay? Or we can introduce a new node here, okay? So here we have beam element plus the spring element. So go ahead and see whether you can be able to determine the deflection, rotation, and reaction forces. And these are the typical solution. I call this typical because maybe assuming there is some error in punching the calculator, you might find a variation. But let's see whether you can get the quantities that I had calculated some years back. And that's it. So you can see it's quite a short session. It's quite a short lecture on beam element. But make sure you know how to derive the equation for the beam element. Now in the next, maybe I believe maybe you might be having another class, but I want to welcome questions. I'm looking at the chat. In the chat area, this class is usually silent. The other years we should have questions in the chat area, or maybe the understanding is quite high. Oh, I get it. It's because I've shared the notes with you early enough. Usually we don't share the note before the lecture, but then I say let's try things differently so that you have gone through them. Anyway, in case of any question, either now or later on, even when you are going, you are revising through this video on your own, you can always ask a question. Usually I prefer people can post it there because I can address it during my free time and other people can also benefit. But sometimes you might have a question which maybe it can't be typed. It can be typed in the comments. So you can end up sending an email. But if you send me an email, then it means I have to see where your workings, so that I can see where you're stuck. I don't know how. I have seen students even from outside Kenya sending me a question, and then I say, this guy is just sending me assignment. No. This is not like Coursera or where do you say? This website where solutions are solved. Of course, we have a channel for that because I realize there are people who are genuinely interested in getting a solution to a problem, but this is outside the classwork. So we have a link where when you go to the download section, because there's somewhere you can go and download all the stuff you're having here. That's where now, based on how your membership, then you can ask a question and it will be solved. But for our classwork, let's do as much practice as possible. If you're stuck, then you can always inquire or consult. So any questions so far? None? All right. If no question, then allow me to stop it at that. I found that even if I give a link, then people just join in and then no questions. Yeah. So I want to get the question from the chat box. All right. I'm looking at the calendar. We are far much gone into the semester. And I wanted us to have our first CAT. So discuss amongst yourself and let me know from your class representative whether between date 30, choose between date 30 and date 4, either Monday or Thursday. I would prefer Monday. It will be a physical one. So I give you 2 weeks for preparation. So either Thursday, date 30th of June. Class rep, take note of that. Choose between date 30 of June or date 4 of July. And class rep, let me know before the end of this week. 30th June or 4th of July. Is that okay, Pascal, and the other member? The other thing is that just to emphasize that by now you should have done something on, it's my hope that you have done something on finite element, especially installing and going through that tutorial. Our CAT will cover up to this place we have covered today. Yeah. Of course, the other material that you are going to cover in the next week will not be that CAT. Yeah? So start doing practices first now. Okay, there being no question, that's the end of today. Thank you for your attendance. Then let's meet next week. Class rep, I'm waiting for your response once you consult with your members. So bye-bye for now.